Okay. So I think last week when we met, we largely focused on the like basically how to find the reactive forces or the reactions. Okay. And in finding reactions, we went through some calculations then so that we could understand the processes or the procedure involved in analyzing such structures. All right. So your tutorial session was also to build on that uh, concept where you could look at the different like different approaches that we can have to solve similar problems. Okay. Um, try to find your tutorial questions from Wednesday. Because I think I have them on this assignment. Okay, yeah. So with the tutorial, let me just start a new page. Okay. Um, so quite a number of them. The idea was to come up with how to analyze a beam. All right. So let me just solve one with you guys, maybe explain it a bit more. Then let's see how it goes. All right. So let's say I have a beam, okay, and it has a UDL. Right. So this is one way to represent the UDL. Either we use a rectangular shape or the whole cloud-like shape is fine. It just means that's how we see UDLs, okay? So the intensity of the load is 4 kilonewtons per meter. Okay. If you have any questions at any point, you can just stop me and then ask your questions. So we have these dimensions. Okay. This is 4 meters, 10 meters, 2 meters, A, B, C, and D, right? And the question says determine uh, the support reactions. Okay. So with our solution, what do? We do the free body diagram. That is the one, the most important thing to do first. Because the free body diagram would help us to, uh, what's the word? Know where our reactions are, and what directions these reactions are in, then we can use that to find our problem. All right. So step one, we draw the free body diagram. Okay. So I take my beam again as it is, then show my support reactions. So I have here these are support reactions. So this becomes my VA, this becomes my HA, then here this is my VD. These are the unknown support reactions, and I have my UDL somewhere in here. Okay. Then I have my distances 4, 10, and 2. All right. So once you have the free body diagram, then the next thing is to use the equilibrium equations. All right. So use the equilibrium equations. And we know three. So first start with summing vertical forces, sorry, horizontal forces. All right. In this case, there's only one horizontal force, which is HA. All right. So summation of horizontal force is supposed to go to 0. So since we only have one, then it means that we equate that one to 0. So HA is 0. All right. Then when we are summing vertical forces to be equal to 0, how many do we have? We have VA1, VD2. Then we also need to convert the UDL here into a load. Then that becomes our third. Okay. So in this case, VA and VD are acting upwards. All right. So I can do that. Okay, then upwards is positive and then downward is negative. So VA plus VD minus. Now, when we look at the UDL, let me just delete something. Okay, so when we look at the UDL is on this section. This way we can find out our UDL. Okay. So to find the total load of the UDL, where the UDL is supposed to be a line load, we need to find the area of this rectangle. That's the idea. Okay. So if I take that apart, this is what I have. Okay. Here's 4, and this distance here is the 10 meters. Sorry, 10 meters, not millimeters. And the height is 4 kilonewton per meter. So here I'm converting the line load to, let's say, a point load. Okay. Let me put point in brackets. Oh, sorry, in inverted commas. Okay. So here is simply multiplying the base. The area of a rectangle is what? Base times height. All right. So it becomes 10 meters times 4 kilonewtons per meter. And this will give me 40 kilonewtons. Okay. Typically, VA and VD will be in kilonewtons. All right. So again, as I explained earlier, we always have to add apples to apples and oranges to oranges. You cannot add oranges to apples. So ensure that you have converted everything into one unit, and then you can sum them up. Okay. So that becomes minus into bracket 10 times 4, which I have over here. All right. Normally, we prefer to write it the 4 first and then the 10, since it's 4 times distance. All right. So this is acting downwards, and that's the reason it is negative in this space. Okay. So all of this will be equal to 0. So VA plus VD will be equal to 40 kilonewtons. Okay. This equation has two unknowns, has VA and has VD, right? From our math class, we learned that if you have two unknowns and you have one equation, pretty much you cannot solve that problem. All right. So two unknowns requires to have two equations at least. Right. So we need to derive a second equation in this case to help us to find either VA or VD. And as a reason, we find moment about some point. Okay. So in this case, let's find moment about point A. Okay. So moment, we understand that moment is when we are finding moment, is what? Force times perpendicular distance. All right. Perpendicular distance. And this distance is between the point of interest. The distance here is between the point of interest and where load is acting. Okay. Like this is very important to us. Okay. So in this case, our point of interest is A. All right. is point A. Then we'll take each load and find out where those loads are acting. Then find the distance between where these loads are acting to point A, and that becomes the distance for the moment. Okay. So let's start with VA. So it becomes VA times the distance, let's call it DA. We'll come back to that. Then we have plus VD, let's say plus or minus VD. Okay, should them not, for now, I'll put any pluses over there. They also have VD times, let's say DD. Okay. Then we have the UDL, all right, which is the UDL load. And we also need to convert that. So it becomes the 4 times 10 times, let's say, DW. All right. So going back, or let me just redraw here to explain to us. So here we have our VA. Here we have our VD. We are taking moment about A. So this is A. This is where we want to find our moment about. All right. So DA is supposed to be the distance between where the load VA is acting and also where the moment is being taken. All right. This case, VA is acting at the same point as the point we want to take the moment about, which then means that our DA here is 0. Okay. Then DD will be the distance between, again, it's vertical distance, so it's a perpendicular distance between where VD is acting in this line to where we want to find A. So this distance here is D, and this distance has to be perpendicular to the load. All right, so they have to form a 90-degree angle over here. Okay. So this DD here is pretty much the entire length of the beam, and that will be 16 meters. So our DD is 16 meters. Okay. Now, when we come to our DW is interesting because we have a distributed load, a UDL, right? So we need to figure out what points that UDL is acting, right? In this case, it is acting over a range, all right? So, but we need to find a particular point. Okay. But since we are also treating the UDL as though it is a rectangle, we know that a rectangle has a center of gravity, all right? In your physics class, I think as part of one of your practicals, you were balancing a ruler or a bar over a knife edge, all right? Pretty much what you are trying to do was to find the center of gravity, right? So that if that ruler is perfectly made, its center of gravity will be at the middle portion of the rectangle, of the ruler, all right? So if you come back and look at a rectangle, its center of gravity is at the midspan. So center of gravity or centroid, right? They are the same. Center of gravity is used for a 3-dimensional object, and then centroid is used for a 2-dimensional object. That's all the difference, but they are about the same, all right? So if we can identify the centroid, then we can use the centroid as the point where the load is supposed to be acting at, okay? So I'm going to just redraw again, just for us to see. So I have my UDL in this space. Okay, this whole thing is 10 meters. And then the center of gravity is right here, half of the 10. All right. So it means that if I'm to convert the UDL into a point load, it's going to act at this midspan. Okay, which means that my DW will be, since here is A, since this is A, then my DW will be the distance between A and where the load is supposed to act, which is supposed to be at its centroid. All right. So my DW here will be this distance from here to here is half of the 10. So this is 5. So if this whole thing is 10, then this is 5. This is also 5. Okay. So we have 5 plus this extra distance here, which I think it's 4. All right. So the total value for DW is 5 plus 4, and that is 9 meters. Okay. So which means that the summation of moment at A will be equal to VA times 0, VD times 16, and then 4 times 10 times 9. Preferably, instead of writing it 9, we prefer to write it this way. It's fine. It's just a thing I do, right? I divided 10 over 2, which will give me the 5 I had earlier, plus the 4. This helps me to know exactly what I'm doing, all right? This portion here also give us 9 anyways. It's the same thing. So all of this, sorry, all of this should be equal to 0. Black pen. All this should be equal to 0, but we are summing, so we're supposed to add, right? How do we know whether some of them is plus or some of them is negative? We use the rotations, all right? Is it clockwise or anti-clockwise? Okay. So let's go back. Now, since A is our point of interest, typically you would hold point A, and then if it's VD you're looking at, you push VD, all right? So if you hold point A and you push VD upwards, which is what we are trying to do, you would realize that it's going to cause the beam to move upwards. So the beam will change to this direction if we apply VD upwards. And this looks like it is moving in the anti-clockwise direction. So VD is counterclockwise. All right. VA times 0 is 0, so it doesn't really play any role over here. Then when we come to the UDL, which gave us 40 kilonewtons, which was 4 times 10 or so, it is acting downwards. Again, we are holding point A, which means that we will deflect the beam. The beam will deflect downwards this way. All right, so that's like holding A as pivot, and that means that the beam will undergo a clockwise rotation. So this whole system here is clockwise. Great. So now you have been able to identify the directions of these loads. The next thing is, what do? You can, if you make clockwise positive, then anti-clockwise should be negative. So uh, if clockwise is positive, then anti-clockwise is negative. Or if you make clockwise negative, then your anti-clockwise should be positive. It's just opposite, right? At least for external loads, reactions, this is what we do. We choose anyone we want to. When we go deeper, we'll just go with a convention or an agreed process. But normally for external reactions, you can decide on which one you want to do, and you end up with the exact same answer. Okay, so let me go with the option. I would prefer option, what's the name? 2, right? So it means that here is positive and this is negative. All right. So I can rewrite and get 16 VD minus what would this give me? Those with the calculators, you can tell me 40 times 9 is what? 360. All right, so all of this is equal to 0. So VD will be equal to 360 over 16, I believe. So I should get 22.5. Yeah. So this is equal to 22.5 kilonewtons. Okay. So now I know my VD, right? So I'm coming back to this, the equation for summation of forces in the y direction, sorry. So now I know VD, I need to find VE. So from previous, we said VA plus V sub D was 40 kilonewtons. Okay. So substitute VD equals 22.5 kilonewtons into above equation. All right. So that it means that I have VA plus 22.5 equals 40. So VA, change of subjects, will be equal to 40 minus 22.5. This will give me a VA of 17.5. Okay. So in this case, these are my reactions. HA is 0, VA is 17.5 kilonewtons, and then VD is also 22.5 kilonewtons. Okay. No, when you're solving a question in exams or whatever, you don't need to state whether it's which options you are choosing in terms of the anti-clockwise or the clockwise directions. It doesn't matter. Your final answer will be the same regardless, so you don't need to state. All right, just solve it and then you end up with the same answer. Okay. So this is what we are supposed to do. All right. As I mean, my steps are a little bit more because I'm trying to explain to you guys what goes into the calculations. But in your case, your steps will be less long, or it won't be that much long compared to mine. And this is the idea. Okay. Is there any other example I need to solve in your? Okay, so let me just solve one example from your tutorial session. So let's say we have what we call a cantilever. So this is a cantilever. It has some UDL on the ends. The height of that UDL is 2 kilonewtons per meter. All right. And these are the divisions for the length. Sorry, my alarm has gone off. Wait, wait. So let's say if you have two UDLs on the beams, the process is the same. All right. Doesn't really the steps are pretty much the same. Uh you treat the two different UDLs as separate. I don't know if was there anything like that in your assignment? I don't remember. Um, I'm pretty sure you're asking because of the assignment I posted. Uh, Let me see your assignment. Yeah, so your assignment has two UDLs on it for question 1B, I believe. Yeah. So it's the same process. There isn't anything different about it. Yeah, thank you. So here, these are the dimensions. So this is 4 meters. This is also 4 meters. Okay. The again, we draw three. Let me call this point A, uh, point B, and point C. Okay. So here with our solution, we start with a free body diagram. Okay. The goal is that we need to know what reactions you are looking at and then what directions these reactions are in. Okay. Normally, since we don't know what they are in, we assume that for a fixed support, there are three reactions, right? Horizontal, vertical reactions, and then a moment, a point moment, as we call it. So we have MA, which is the moment at A that we don't know. Then we have HA, and we have VA. Again, reactions are what oppositions to movement. All right. So normally when you apply a load to any structure, the load can cause the structure to move left and right. So that's horizontally, right? That it can also cause it to move up and down, that is vertically. Or like how you open the door, it can cause it to rotate about its axis, right? So you can have, let's say, a bar, and then maybe you hold this point. Okay, this is even, let's say we have a bar and you hold this point, you apply some load to it, right? So if you're holding this point, so let's say you are holding here, you would realize that the bar would sometimes be here, be here, be here, and be here. So pretty much the bar is rotating, right? It's rotating about a point. Okay. So it can move sideways, it can move up and down, and it can rotate. All right. That's how mostly structures behave. So we place the support in there to prevent any of these movements. Okay. So a fixed support will prevent all three types of movements: no sideways, no up and down, and no rotation. So once it prevents these three movements, it needs to provide a reaction, right? Action and reaction are equal and opposite. And when that happens, there's no change in the original state of the structure, which is what we want. So we need to find what these reactions are. So for a fixed support, there are three: MA, HA, and then VA. Okay. So we still have our load here. And this is acting downwards. Okay. So now let's sum forces and see what we have. Okay. So summation of horizontal forces equals 0. So you sum all of them. And there's only one horizontal force, HA. Okay. So in this case, our HA is 0. Again, HA is not always 0. It's not cast in stone that is always going to be 0. It depends on the loads that we have. Now, when we sum the vertical forces to be equal to 0, there are only two of them. So there's the VA, which is vertical, and we have the UDL, which is also a vertical load, right? The VA is acting upwards, and then the vertical load is acting downwards. You only have one support in this case, and the support is supposed to be the support at A, which is a fixed support. So this here is a fixed support. There is no support at B. There's no support at C. Okay. And this is an example of a balcony, right? So if you have ever been to these story buildings, you'll see that if you have your room on some of the upper floors, you'll see that so if your window is somewhere here, or your door is you have a door somewhere here, you can literally walk to a section attached to the building, which is outside of your building where you stand in there. All right. So the way we join, the way we join that together pretty much ends up forming what we call what we call a sorry, my voice. What we call a cantilever. All right. Let me see if I can show you guys examples of what that is. Let's try to get you guys a picture or something. So I think some of your hostels might even have uh, such such ships or such balconies. All right. Uh, so this is not too clear, but just for us to see. All right. So on the outside of this building, we have these things here. All right. All of these things here, and pretty much these are the balconies. All right. That I mentioned. There's so many of them. All right. Okay. That's enough. Right. So it's like they are protruding outside of the building. And if you look at it carefully, this is the line diagram of this structure. Okay. It is a cantilever. And that's how we design some of these things. So this load you can see over here, it could be maybe some machinery or some item that has been placed on the balcony, for example. Okay. Normally, balconies are not this long. An 8 meter long balcony is a very long balcony, and the design can be challenging. All right, not impossible, but challenging. Okay. So now let's sum all the vertical forces together. Um, VA is going upwards minus this coming downwards. Again, this is a UDL. So we need to convert this line load or this UDL into a point load. All right. So again, this is like what? A rectangle. All right. The height is 2 kilonewtons per meter. And then the width is 4 meters. So finding the area of the rectangle would be what? Let me do 2 times 4. And this can be equal to 0. So here, one equation, one unknown, we can find the unknown. That's uh, how straightforward it will be, right, in terms of equations and all of that. So here, VA will be equal to 8 kilonewtons. So found VA. So now we know VA, but we don't know MA. So we need to find MA. Right? This is one of the unknowns as well, right? MA is what we call a point moment. So the same way we have point loads, we can have a point moment or a couple, all right? When you apply some rotation to a material, pretty much you're applying a couple, which is in its own way a point moment. Uh, so to find MA, please, summation of moment about A is not the same as MA. All right, so let me explain that so that we understand. MA here is what we call a point moment. Okay, so that's like a load. All right. Then when you say summation of moment about A, it means that you are adding all forces plus their distances, end point moments about point A. So that's the difference between the two. One is a moment, a standalone value, and then one means that you are summing up all these standalone values together at a point. Okay. And that summation should give us 0 because we want to maintain equilibrium. All right. So if you sum moment about A to be equal to 0, it means that we can look at it in this form. Since VA is acting at A, it means that the moment due to the load VA is 0. Take note. But there's a point moment, MA. And an existing moment doesn't need distance. It already exists, right? So distance will not have any influence on it. Okay. So that when it comes to moment, we will have so there'll be a point moment MA, which is acting clockwise. Then there'll also be the moment due to the UDL. Again, the load of the UDL is 2 times 4. The distance will be half the distance the UDL is acting at plus whatever remaining that you have. All right. So in this case, my UDL is likely to act in this space over here. So half of this distance here is 2. So 2 plus the remaining distance, right? So half of 4 is 2. So 4 over 2 is half of 4. Plus the remaining distance of 4. Okay. Again, this is what's clockwise, right? So they both are the same direction. So I could just say plus, plus, and I'm good to go. Okay. So here in that case, my MA will be equal to negative 2 times 4 times, this is going to be 6. All right. So this will be negative 48 kilonewton meter. The negative here that we see indicates direction. It indicates direction. What this simply means is that the direction you chose your MA to be in should have been the opposite. So initially we assumed that MA was clockwise. By the end, we got a negative value. So it means that MA is actually, in fact, anti-clockwise. All right. So sometimes through experience, somebody would prefer that when they are trying to draw the unknown reactions for the moment, they do it anti-clockwise, which is fine. All right. Which means that if your MA is initially anti-clockwise, that means that you end up with an MA value being equal to 48 kilonewtons meter, which is fine. It works. They both are correct. The only challenge with that, which you'll get to see going forward, is that our goal is not only to find reactions, right? But it's to take that information to find how the beam behaves internally. So like how the inside of the beam behaves. So the internal behavior of the beam, right? And then we need to look at things like shear force and bending moment and all of that. And through experience, it's best to assume that MA is always clockwise. Assume it's clockwise. Then later when you find it to be anti-clockwise, it's actually going to help you to draw some diagrams, or it makes it easier to draw some of these diagrams. Yeah. So HA, VA, MA, you can decide whichever directions they are going in. It's up to you. You can even make VA act downwards, or you can make HA act towards the left. It's fine. And this is the reason why we need a free body diagram, right? Because Kwesi can choose a different direction, Miracle can choose a different direction, but how would I know which directions Kwesi and Miracle have chosen? Unless they draw the free body diagram. Okay. So for basic structures, free body diagrams are very important. And I would encourage you guys to keep doing them because, well, one, you get marks for it, obviously. But then two, it takes away every form of confusion. All right. Even in the field, takes away confusion. When somebody sees your work, they check your free body diagram, they understand pretty much your calculations. All right. And one thing you wouldn't want as an engineer is to create ambiguity in your work. Once your work is ambiguous, it means that people can interpret it the way they want, and they'll end up putting out structures that might not be what you want. So, Elvis, I've been trying to answer the question on the direction of the point moment. That it doesn't really matter. You can choose it to be clockwise or anti-clockwise. It's up to you. And it's the reason why we need a free body diagram. The free body diagram will tell me what direction you chose your uh, reaction moment at A to B, right? Preferably, choose them to be clockwise. It saves you some issues or it doesn't make things complex down the line, at least per experience that I've had, all right? But you can still decide to make it counterclockwise if you are fine with it. But just so that down the line, you will have to tweak the way you understand a few things here and there, which is also fine. Um, what again? Yeah, so I think these two examples should help us to understand the analysis of beams using the analysis of beams with this approach. All right, statically determinate structures. So if you go to vCampus, which I think every one of you guys should be there by now, is that there are three things over there. The lecture videos are there, which is on YouTube, obviously. Then any note I write in class on the screen, in this case, I also posted over there. Then I also have pre-typed, already typed lecture notes, which I also post. So you have two different lecture notes, pre-typed, and then or pre whatever, pre compiled lecture notes already there, typed in PDF, everything nicely typed. Then I have the handwritten ones. So there are two sets of notes that you need. The two should be adequate to explain the concept to you. And then our texts, our book of reference is the structural analysis book by R.C. Hibler. So that's our reference. Pretty much everything I'll be discussing with you guys can be found in there as well. All right. So if you have this, the videos, you have the Hibla, you have the two lecture notes, it should be adequate to understand the class. I mean the course and then do very well in it. You can also, I mean, advance your knowledge base by watching some YouTube videos. There are so many of them out there. Or if you go to the library, I think on the same block, the F block, first floor, you'll find books on structure and analysis. There is the Todd, there is the what's the name? The Bavigati also, this interesting book and all of that. There are so many books out there. All right. Okay. Um, Let me just quickly check something. If I'm hoping we discussed that the last time we met. I'm guessing we looked at the different types of beams the last time. I'm hoping we did. Doesn't look like it. Okay. Oh yeah, yeah, we did the types of beams. Yeah, so we have the simple supported beams, the overhanging, the cantilever, and also the continuous beams, which is not what we will do this semester. All right. Okay, great. So I think we saw some examples that we can look at. Uh, this should help us to analyze the structures a bit more. Right. So again, if you have any questions, just let me know. Um, then we can move on with it. Um, are there any YouTube channels that I know? Okay, I'll look for some around and see. Yeah, sometimes the information online, some of them are just not of high quality, which is true, right? So I'll see about that and see if I can find any for you guys. All right. So please, I want to be sure that we understand what is happening. Okay. I think we're about 17 or 18 in the class. We need to understand what is happening. It is important we do. Okay, let's move on to the next topic. Let's see what we have. All right. So far, all that we've been dealing with has been external behavior, right? So we've been looking at external response. Let me put it that way. Okay. So we have the beam. All right. We don't touch the beam. What we look at is the loads which are on the beam. So we focus on loads on beams. So these are the loads on the beams. Then we look at the supports, right? So these are the supports. And then we find the reactions of the supports. Okay. So that's what we've been doing, I think from Monday till today. So we're looking at loads and support reactions. Okay. So primarily we've been focusing on Newton's third law. Okay. That actions are equal to reactions, pretty much. So our loads here are the actions, right? And that's what we've been doing. But then it is critical to understand that before the loads are transferred to the supports for us to have reactions, okay, the loads would have to go through the beams. So the loads move through the beams, all right, to the supports, which means that the beams should also be able to transfer the loads within itself. Okay. Um, for example, so let me go through this process. If you carry a bag of cement on your head, all right, the ground is the support, the cement is the load. You, the human being standing there, you are the beam, all right? So far, what we've been doing is to look at the cement load and look at the ground as the reactions, right? But definitely the load will have to be transferred through your body to the ground. So you feel some pains or some whatever in your head, you feel some in your neck, you might even feel some in your back, and even also some in your calf, all right? This is the load being transferred through your body. And what that simply means is that if at some instant in time, some part of your body cannot support the loads coming. For example, let's say your neck can't support the load coming. You would what's the name? You might cause the cement bag to fall down, right? Because your neck cannot support it. Or if it is your back, you might want to bend down, the cement bag will fall down. If it's your knee, you buckle, cement bag will fall down, right? The ground is still fine. The ground is still okay, but the conduits, the media through which the load is being transferred or the cement bag is being transferred is not adequate enough to receive or to transfer that load. So we also need to know how the inside or the internal material, so in this case, how your bones, how your blood, how your whatever are, to see if they can even transfer the the bag of cement. All right. So in the same way, when it comes to beams, we also want to know um, the behavior internally of the beams or of the structural member to see if they can transfer these loads to the support. Okay. So for that reason, we need to understand, we need to study what we call sorry, the internal forces in the structures or in the structure. Okay. So our next topic will be uh, internal forces in the structures. Okay. So we have three main types of those internal forces, and then we would explain the concept behind them. Yeah. So pretty much during the transfer process, we internal forces are developed. Okay. Uh, and these internal forces, we define these internal forces as three. There are three of them. We have the axial forces. Okay. They are typically for beams, they are horizontal, right? Or so for beams, they are horizontal. Okay, how to put that caveat in there. Then we have the shear forces. Okay, again for beams, these are usually vertical. Then we have the bending moment. Okay. Um, so when we're looking at equilibrium, right? When we study the equilibrium or the right? With equations, we said that what when we are summing whatever it's horizontal or whether it's the moment about a point should be equal to zero, right? So that's the idea, right? So externally, the building or the structure should be in equilibrium in the sense that the loads and then the reaction should give you a net zero force behavior so that the structure remains in its state of rest. So that is a equilibrium, right? As much as you also want the overall loads and reactions to be in equilibrium, you also want the internal behavior of your uh, beam, in this case, to also remain in equilibrium. All right. So, all right. When you have a beam, right, it's made up of fibers, like series of small elements. So let me say it in layman terms, atoms or elements or compounds, right? Or molecules which are joined together. All right. So these molecules which are joined together are also exerting forces amongst themselves. All right. And these forces are giving us a net zero, and that's how come you have your material as it is. For example, if it is a concrete beam or a wood beam, the reason why the wood beam looks the way as it is in front of us is because the molecules within the wood or the cells within the wood are the loads between them are the same, or the forces act in that the molecules are interacting amongst themselves. When you sum them up, you get zero. All right. So some of the forces are axial, horizontal if they are beams, or they are shear, vertical if they are beams. And also we have the moment, which we call the bending moment. All right. So for example, if I cut, let's say I have this beam, okay, just to explain the concept to us. If I cut through the beam, right, I maybe take a knife or whatever and I cut through the beam, pretty much what's going to happen is that I'll have two separate beams, right? So I have a beam on the left with a cut surface, the other beam on the right. Let me just move here with a cut surface. Okay. So we have these different sets of beams. Okay. So once you cut them apart, you expose the forces that were keeping the beam together. Okay, that's the basic way to explain it. And these forces that you exposed are pretty much the forces within the material. Okay. And these are the internal forces. All right. So you'll find that you had this here, you had that over here. So that's your H, your axial force, or your horizontal forces. When they were together, when they sum up, you get zero. All right. So once you break them apart, you see what they are. One going towards the right and one going towards the left. Okay. Then you also have shear. Let's call that V. Okay. So again, you also have mostly prefer to have this one going down, this one going up. It doesn't really change anything, just so that going forward it's easier to explain things. Right. So one going up, one going down. Again, if you sum them up, you still get zero, right? Because Newton's third law is playing a critical role over here. Then you also have moments. Okay. So the moment here is what we call the bending moment. So let's make it be a bending moment. Okay. So anytime you cut any point along your beam, you'll find these behavior. All right. So these behavior are what we call the internal forces in the beam. Okay. And we need to determine what the internal forces are, which means that uh, it is possible that if you cut different sections of the beam, the internal behavior can be different. It can be the same or it can be different, right? It depends largely on the kind of loads that you have on the beam. And also on the beam's material properties. But for now, let's just put that on the side. So usually it depends largely on the kind of loads. All right. So what we need to do is that, okay, we need to know if the beam can transfer the loads. That is the whole idea. So we need to find the internal behavior pretty much at every point along the entire beam. Okay. Every point on the beam seems impractical. So what we do that we look at specific points which might be critical to us, and then we use that to determine the forces, I mean the internal forces in the beams. Okay. So if you look at this carefully, the resultant forces will always be zero. All right. So if it's H, you get zero. If it's V, you get zero. If it's BM, you get zero. I mean, at any moment. All right. Okay. So let's just go deeper, explain what axial forces are a bit more, what shear forces are, and also what bending moments are. Okay. So let's look at the axial forces. So these are internal forces. Please take a note. When you look at reactions, we have horizontal reactions. Yeah. The axial forces are also in the same horizontal directions, but they are separate from the horizontal reactions. The reactions are external, they are outside uh, the, the structure or the beam in this case. Whilst the axial force here, it is inside the structure. It's good to always know this distinction because it requires us to do a few things going forward. Okay. What time does this class end? Just in the number. Do you know when it ends? Just want to know what to do with the time. Okay, so we end in the next 30 minutes. Okay, all right. Thank you for the update, all of you. Okay, so let me just look at axial forces quickly. Let's see what we can do. Um, so we have two main types of axial forces, right? Two main types. We have tensile and then we have compressive. Okay, so if for the same beam, I have a force acting this way, so it's trying to push towards the beam. This is what we call a compressive axial force. Okay. Simply put, it's trying to crush the beam or the bar. It's trying to reduce or shorten its length. All right. So compressive axial forces is here to shorten the length. Okay. Then if you have the same bar, okay, but in this case, the force is moving away from that beam. Then this is what you call tensile axial forces, or we can just say tension, right? Some would say compression tension is the same thing. Here, the goal is to elongate the bar, or to increase the length of the bar, or maybe beam, depends on which way you want to look at. So what this means that if you have the original length here, let's say L naught, for high compressive forces, with time, you have a new length here, L1, because this end, this zone here, has been pushed inside. All right. For the tensile, if your original length was L naught, with time, your L1 would have gone a little bit beyond because there's been some addition because of the elongation that would experience. All right. Let me see this. And then the questions in the chat, no, not yet. Okay. So we define an axial force as any force tending to produce an elongation or any contraction failure at a given point in the beam. All right. So at any given point along the length of the beam, we can determine what the axial force might be. Right. It could be tensile, it could be compressive. Almost all the time, not almost all the time, but usually for beams, axial forces tend to be a bit negligible, right? Uh, because beams are normally loaded with vertical loads. Again, so the definition for axial forces, it's in the type lecture notes anyways. So axial forces, or so there are the forces. Let me just put here. Oops, tending to produce elongation or contraction. A given point in the beam. So the whole idea is that, okay, you have these external loads acting on the beam. What would be the component of these external loads within the beam that can cause the beam to be close to failing, right? Or at the point of failure, right? And there are three of these internal behavior. The axial force is what we are looking at currently. All right. Now let's look at the shear force. I think I have some 15 minutes. Okay. So we define the shear force as pretty much a cutting or a slicing action, right? Cutting or slicing action, which causes the beam to snap. All the notes are already on the V campus, so if you've not been there, then that's different. But all notes that you need for this course would be provided on the V campus. So please go there. It should be your go-to spot for any of my courses that you are taking this semester. Okay. So normally, the failure for axial force can either be contraction or expansion. But the failure for shear forces is where you have, so let's say if you have a beam and you have very high, let's say you have maybe very high loads, let me call this load P. P is very large, okay? And at the point where P acts, it can cause the what's the name? The beam to break apart, right? For one to shift down and one to shift up, or more or less. So in effect, you end up with a situation like this. Let me just draw this on the side. This way. Okay. So this end here, there has been a slicing behavior. All right. So that is what we mean by the slicing behavior. And to find so whether it is shear force, it's axial force, it is bending moment, we can determine what the bending moment, the shear force or the axial force would be at any point along the beam. Okay, which I'll talk about when I deal with all three of them. Um, so the shear force can act upwards or downwards. Okay, so let's take notes. Okay. So what this means is that I can have my sharing behavior either this form or I can have it in this form. Okay, where depending on what the load direction might be, I can end up with. So this is more or less like a downward behavior, and this is an upward behavior. Uh, yeah, I'm taking into consideration this section. All right. So I'm looking at this section anyways. That's what I'm using to tell whether it is upward or downwards. I mean, just to explain the concept to us. You can use the left side, and then with the left side, this will be here will be upwards, here will be upwards, and here will be downwards. It's fine. It works just the same way. All right. Let's take a note of that. All right. Definitely for us to have that slicing effect, it means that one should drop below the other, pretty much. Right. So anytime we have sharing behavior, it means that one is dropping below the other, or one is moving above the other, right? Even if they move up together or if they move down together, there will still be difference in their movements. Maybe one will move slightly down and one will move more down. At the end of the day, you still have one moving lower than the other. All right. Um, the other concept will be the bending moment. And so with the bending moment, this is because usually when you have a beam and you subject the beam to any load, when you subject a beam to a load, it deforms. All right. So again, if you have this bar, um, or this beam, for example, it's not a bar, it's a beam. If you have this beam, for example, like this, all right. If you apply some loads to it, it can be any load, right? For example, your beam will deflect. Okay. Beams deflect. So this is how the beam will deflect. It will bend. All right. So this is the bending process for beams. Uh, and this bending is occurring because of the internal bending moment in the beam. All right. So the way to define a bending moment, so bending moment can be defined as the magnitude of the bending effect in the beam. Okay. So, for example, we can determine the bending moment at this point. Let's say point one. We can determine the bending moment at point two, point three, point four, point five, and maybe point six. All right. And at each instant in time or at each location on the beam, the bending moment will be different. Right. The bending behavior will be different. Okay. Normally, it means that around between 3 and 4 is where you might have your highest bending moment value, right? At least for this case, all right? And just like our structure, uh, we can have we can have clockwise and counterclockwise uh, bending moments. Okay, so let's take note of that. The units for shear force is in either newtons or kilonewtons, no, newtons or kilonewton. The same for axial is also newtons or kilonewton. For bending moment, the units is in Newton millimeter or kilonewton meter. Mostly you find us using the kilonewton meter a lot. Uh, so normally with all of these, we need to draw diagrams, all right? So typically we draw diagrams. As I said, if you want to know the behavior, the overall behavior of the beam, right, we need to know, let's say, for example, if it's shear force we are looking at, we need to know the shear force at every point along the length of the beam. Again, that is impractical, nearly impossible to do that. So why don't we find, for example, the shear force at critical point along the beam, and then draw a diagram, and that diagram will actually show the shear force on the entire beam. All right. Then we'll know where the highest shear force would be, which is pretty much at that point is where we are likely to see failure, if there's going to be any, and then how to prevent that from happening. Okay. Because if you have loads on your beams, all right, but then let's say, for example, the shear force at some point in your beam is so high, the beam can fail. And if the beam fails, your load cannot be transferred to the support, right? And it means that your beam no longer becomes a structure. Okay. And our definition of a structure, we mentioned that it should be able to transfer the loads without collapsing. So once that object collapses, it then means we no longer have a structure. Okay. And the way we calculate these values is that we use we use the um, algebraic sum. All right. So whether it's axial force, whether it's uh, shear force, whatever it is, if it's So for example, if it's shear force, for example, the algebraic sum algebra is just additions, right? Uh, we are saying algebraic because normally there are pluses and minuses in there, right? Um, so if you want to find the bending moment or the shear or axial force at any point, definitely you have to cut the section at that point. Okay. So if you cut a section at that point, you can choose any of the halves to find it. Okay, so let's go in, going back here. Um, if you cut the section, so let's say we want to find the shear force at, let's say, XX, right? So we break the beam apart at that point, and we want to find the shear force V. We can either use the left-hand side or the right-hand side to solve it. In that way, we'll still get the same V, right? So if you want to use the left-hand side, which I think it's usually the one that we go with, it's fine. If you want to use the right-hand side, it's also fine, all right? So what we mean by the algebraic sum is that we sum up. So for example, shear force, we sum up all forces, or in this case, all vertical forces, because that's what we define as shear, all vertical forces, um, whether they are upward or downwards. We sum them up. Okay. Upwards or downwards, either to okay, so let me do it this way. To the left of a point, okay, on the beam. Okay. And this is working because we are using the left-hand side. If we're using the right-hand side, it becomes to the right uh, of, of a point, not to the right of a point on the beam. Okay. So again, this will be the right-hand side. So the most common you'll find us going with is, oops, the blue. Sorry. Um, so the most common is the right-hand side. So this is for um, shear force. If it were for axial forces, then we would say that then any axial force is the algebraic sum. This is also the sum of all horizontal forces. And again, this can be forces either to the right or to the left, to right or left. And then the reason why I did this way because if I say left and right, it gets to confuse us a little bit. Then two again to the left of a point on the beam. Okay. So it's the same thing as the left-hand side or to the right of a point on the beam. So this is the right-hand side. Again, usually the most common you find people going with is the left-hand side. So let me just put that also for the bending moment. So for the bending moment, the algebraic sum, the sum of all moments, okay, either clockwise or, sorry, it's not even always end, clockwise and counterclockwise. So it's not, I shouldn't be saying all because like I'm trying to choose one. Okay, so most of these things should be end and not all. This should also be end and not all. Okay. So again, to the left of a point on the beam. So again, here we are looking at the left-hand side or to the right of a point on the beam. Okay, so there's a right-hand side. Um, Again, the bending moments rule is quite, I mean, so with the axial forces, we have a sign convention rule to play. That comes into focus. So let me just put that over here, then we can end the class, all right? Because I want you guys to think about that throughout the week. So for the so with this one, we use a sign convention, all right? When you are dealing with external reactions, you decide what directions your reactions are in, and then you solve for them, right? So here, if it's clockwise, it can be positive or negative. It's up to you. Take note, when finding reactions, you more or less decide what directions you want your reactions to be in. But when we are dealing with the internal forces, the internal behavior of the structure, we work with a sign convention. We all agree that this is the way to go, and then we go by that. All right. So let's say if this is my point, okay, so the point I've been talking about, if this is a point on a beam, okay. If you're looking at axial forces, okay, so with the left-hand side for axial forces, it means that on the left of the beam, you either have the beam going this way. Sorry, I mean, you have the forces on the beams going towards the left, or for that same point, you can have the forces going towards the right. All right. These are the forces that you can have on the right, on the left-hand side. Okay. And then we are saying that if it's going towards the left on the left-hand side, then this is positive. Okay. Now this is negative. Okay. So in a way, we are treating tensile as positive and then compression as negative. Okay. So what if you're also looking at the right-hand side of the structure and not the left-hand side? So on the right-hand side for the same point, for the same two sets of points, that means that you would have this going here and also have that coming here. Okay. So if this is the if these are the lows on it, then again, this is positive, and here we have negative. Okay. So what if you are looking at shear forces? So let's look at the left-hand side and again the right-hand side. Okay. So again, these are my points. These points do not, or these are the points we want to find our shear about. So let me just draw them over here. So on the left-hand side, all our forces, if we have a force going up on the left, you have a force going down on the left again. So if it's upward on the left, then that is what? Positive. If it's downward on the left, that is negative. Okay. So on the right, we'll have this. Um, this is down, and then we have this up. Okay. So again, if it's on the right and it's going downward, it is positive. And if the forces or the loads on the right are upward, that becomes negative. Okay. Then the last bit will be the bending moment. So again, the left-hand side. Let me oops. The left-hand side, and then the right-hand side. So let me just divide that into two. Okay. Again, the same points. So if it's on the if it's on the left side and it's clockwise, so this is clockwise. Okay. Or if it's on the left side and this is counterclockwise, so this is counter, or anti-clockwise, it's the same thing. Then this is positive, and then this is negative. Okay. Then here, if it's counterclockwise, so this is counter clockwise, and here, if this is clockwise, then the counterclockwise on the right is positive if you're looking at the right-hand side, and then it's negative if you're looking at the left-hand side. Sorry, negative if you're looking at the clockwise on the right-hand side. Okay. So I'm going to end over here. Just go through whatever we have discussed today. I'm sure if we meet again Monday, we'll go deeper into how to use. So someone wants to know why the sign change with the direction and position. Yeah. So how do I answer this? So this is the reason is because anytime so going back to the very beginning, when you have a beam, okay, and you cut a section or you cut the beam into two, pretty much what you see is that, of course, you cannot see that with your naked eye anyways. Uh, but what you see is that if you cut it and then there is a force acting downwards on the left section of the beam, you will have an upward and equal direction. All right. So that if, let's say, this is your point of interest this way, it means that on both sides, on the left side, if there's a downward force on the left side, you have an upward force on the right side. That is how we maintain equilibrium. All right. So that if on the left side, this value is, let's say, maybe negative 20, then here should also be negative 20. All right. So that when you sum them up, you get 0. And the summing is simply minus 20 minus into bracket minus 20, and that'll give us 0. Okay. If the minuses are too much, let me just go with the plus. It's fine. So that if this is, let's say, 40, this is also equal to 40. And because they're in opposite direction, if one is positive, the other will be negative, and that'll give us 0, right? So that is the general idea, all right? The reason I use negatives because for the first one was because we have established that when you have the force acting downwards and it's on the left of the structure, it is negative. So this point here is downwards, so it's negative. So there should be an equal and opposite reaction on the other side. And that's like how we have this going up. So while this is going up, we have taken care of that negative direction, which is upwards. So they will have the same magnitude. So if one is minus 20, the other will also be minus 20. All right. So in effect, I can take these two guys over here, and then simplify them here, which you find in the notes that if I have this point like this, then it means that I have a downward force on the left and then an upward force on the right, and both of them are negative, okay, which is what I'm trying to explain over here. All right, all right, all right. Any more questions? Let's try and go through this. I've posted the entire lecture notes that we need for everything on this section. So from rigid body, statics to forces, moments, to types of loads, to what a structure is, types of beams, uh, beams with reactions, and also the internal behavior. So we actually have an entire lecture notes on the V campus for that, which you can go through to give you a better explanation, or better at least additional explanation, right? And hopefully Monday when we meet, we'll see what we need to do. All right. For the assignment, let's try and get it done and submit it to the TS. Please take notes. Okay, let me just end the recording.